Hey guys, so today we're going to talk about technology and map making. So there are all kinds of different types of maps that we can use, and today we are going to talk about the different kinds and what they all do. So first off, we have general use maps. So these are the maps that most everyone uses. So there's different kinds of those as well. So there's physical maps that use lines and shading and color to indicate features like mountains and lakes and streams. And then there's relief maps, which use shading and shadows to identify mountains and flat areas. And then we have political maps, which show all the boundaries. So they can be boundaries between countries or states or counties or townships. And boundaries can be shown in different colors to indicate different areas. And then we have a road map, which everyone should be familiar with, which can show you interstates or a bunch of roads, from 4-lane expressways to gravel roads. But maps are useful in helping you find your way wherever you're going. So another type of map is a topographic map. So if you were hiking across the United States, you might want to follow level terrain. If you were piloting an airplane across the United States, you would definitely want to fly higher than a mountain. You definitely don't want to crash into a mountain. Showing you how high or low land features are is a feature of one kind of specialty map. And the shape of the land surface is called topography. So a topographic map shows the detailed shapes of Earth's surface along with its natural and human-made features. It helps give you a picture of what the landscape looks like without actually seeing it. The topographic map of Devil's Tower in Figure 9 shows you the details that you cannot see in the photo. So here you see Devil's Tower, and then here is the map of it, okay? So let's talk about elevation and relief. So the height above sea level of any point on Earth's surface is its elevation. So for example, Mount Rainier in Washington is 4,392 meters above sea level. And the city of Olympia, Washington, is about 43 meters above sea level. So the difference in elevation between the highest and lowest points in an area is called relief. So for example, the relief between Mount Rainier and Olympia is calculated as 4,392 meters minus 43 meters equals 4,349 meters. So this number here, 4,349, would be the relief. So contour lines are lines on a topographic map that connect points of equal elevation. So similar to lines of latitude and longitude, contour lines do not really exist on Earth's surface. So using contour lines, you can measure both elevation and relief on a topographic map. If the top of Devil's Tower is 5,112 feet and the base is 4,400 feet, what is the relief? Okay, so contour lines represent a mountain shown in Figure 10. Okay, so this is Figure 10 here. So these contour lines, they represent a mountain. Now notice that the elevation is not written on every contour line. The darker contour lines, called index contours, are labeled with elevation. How do you find the elevation of contours other than by using index contours? Well, you need to know the elevation difference between the lines. So the elevation difference between contours that are next to each other is called the contour interval. So the map in Figure 10 here, they have different contour intervals of 50 meters. So you can find the elevation of an unlabeled contour by using the numbered index contours. So first you find the closest index contour below the contour you are identifying. Then count up by 50s. So say you're looking at this one here, right? It's 2,100 meters. So to go up, we're going to count by 50, but we're actually subtracting. So let's go the other way so I don't confuse you. So let's start at this 1,900 meters here, okay? We want to know this line. Well, this line doesn't have a label. Well, if we count up by 50s, this one would be 1,950 meters, okay? So notice that a contour line at the top of the mountain forms a small enclosed loop, okay? with a dot in the middle of it, right here. So this dot represents the highest point of the mountain, 2,227 meters, right here. The V-shaped contours pointing downhill indicate ridges, so that's here. And a small V pointing uphill indicates a stream, valley, or drainage, so that's the here. The spacing of contours indicates slope, and slope is a measure of the steepness of the land. If the contours are spaced far apart, the slope is gradual or flat. If the contours are close together, the slope is steep. So here, where all these contours are super close together, that means this side is very, very steep. So symbols on topographic maps. The United States Geological Survey has been responsible for mapping the United States since the late 1800s. And most topographic maps that you see are made by the USGS. And so Table 1, right here, shows some of the symbols that can be used on maps. Okay, so we have like highway, secondary highway, streams, wooded marsh, urban area, right? So contour lines are brown on land and blue underwater, and green indicates vegetation like woods or fields. And then water in rivers, lakes, or oceans are shown in blue, obviously. Buildings are represented as black squares or rectangles, so like this. Except in cities where pink shading indicates dense housing, meaning there's lots of houses. If information has been updated since the original map was made, it is added in purple. So another kind of specialty map is a geologic map. Now, these maps show the surface geology of a mapped area. So this can include rock types, their ages, locations of faults, and so on. The geologic map in Figure 11 here is the geology of the Grand Canyon. So geologic formations on a geologic map, different colors and symbols represent different geologic formations. A geologic formation is a rock unit with similar origins, rock type, and age. So the map legend lists the colors and symbols along with the age of the rock formation. The colors do not indicate the rock's true colors, they just show the many formations that are on the map. So let's find the Kaibab limestone here. Let's find this on the map. Okay? This is going to be this light blue line here, okay? It tells you that this limestone rock was made during the Permian period, okay? So sometimes geologists need to know what the rocks are like underground as well as on the surface. Information can be gathered by drilling for samples, studying earthquake waves, or looking at cliffs. A cliff face is like a profile view of the ground, so geologists can use this information to produce a profile view of the rocks below the ground. So see here, they're going to use this mountain here, and they're going to look at it to create a diagram. So the diagram here, it's showing you like a slice into it, okay? So for centuries, map makers made observations of Earth and gathered information from explorers. First, map makers and explorers used instruments such as a compass, a telescope, and a sextant, which is used to find latitude. And that was used to make and record measurements. So then the map makers carefully drew new maps by hand. Today, we obviously use computers and data from satellites. We've come a long way. One important resource for map makers today is the Global Positioning System, GPS. So GPS is a group of satellites used for navigation. So as shown in Figure 13, down here, 24 GPS satellites orbit Earth, and signals are sent from devices on the surface and they are returned to Earth. The relayed signals are used to calculate the distance to the satellite based on the average time of the signal. The devices may be handheld units like your phone or larger units like the one in figure 14, which will be on the next page. At any given time, a GPS unit receives signals from 3 or 4 different satellites, and then the receiver quickly calculates its location, its latitude, longitude, and altitude. And GPS is used by map makers to accurately locate reference points. So here's a larger GPS unit, which is like a portable one that you can put in your car. Like some of the newer cars have like a screen already built in where you can, see the navigation on it. That's what it's talking about here. So originally designed for military purposes, it is now continuously available service for everyone worldwide. Airplanes, ships, and cars all have navigational systems that use GPS technology. People can find their way to restaurants, hotels, sporting events, and home again. Other uses include tracking wildlife or scientific data collection, detecting earthquakes, hiking, biking, and land surveying. Figure 14 shows a portable GPS receiver. Like I said, you can clip it to your car, but most cars have them in there now, or most people use their phones if they don't have them in your car already. GPS technology continues to improve. Land-based units used in combination with satellites that are already being used to pinpoint people and places to the centimeter. Future improvement will include additional civil channels projected to improve safety and rescue operations, and eventually could be used to guide self-driven automobiles. So Geographic Information Systems, GIS, are computerized information systems used to store and analyze map data. GIS combine data collected from many different sources, including satellite scanners and aerial photographs. Aerial photographs are taken from above the ground, and data collection that at one time took months now only takes hours or sometimes minutes. Map makers use GIS to analyze and organize those data and then create digital maps. And one of the features of GIS is that it creates different map layers of the same location. So if you look here, there's the area is mapped, and you can see the elevation map, the land usage map, and just the road map. So imagine setting up a model for an airplane landing under certain weather conditions using GIS. So database view begins the process by assembling information from existing database on winds, airplane flight, landing procedures, and airport layouts. Then the map would draw from a set of interactive digital maps that show features and their relationship to Earth's surface. And then a model view would pull all the information together so you could run simulations under changing weather conditions. So you could use this map to look at what a runway would look like if it were wet, or if it were snow covered, or really hot, right? So let's talk a bit about remote sensing. A cup of hot chocolate looks very hot. You place your hand over it and you can feel the heat from the liquid. Without even touching it, you know it's still too hot to drink. You have just avoided burning your mouth by using remote sensing. So remote sensing is the process of collecting information about an area without coming into physical contact with it. There are many applications for remote sensing. The process produces maps that show detailed information about agriculture, forestry, geology, land use, and many other subjects. Often, these maps cover huge areas. Map making was transformed when it became possible to take aerial photographs from airplanes. Now, an even more powerful type of remote sensing is being used. Since the 1970s, satellites orbiting thousands of kilometers above Earth's surface have been used to collect data. Monitoring change with remote sensing. So satellites orbit Earth constantly, repeatedly. They don't stop. So this means images of location or a location made at different times can be used to study change. So for example, in 2005, Hurricane Katrina struck the Gulf Coast. Before and after images of the Mississippi River Delta region are shown in figure 16, so down here. Images like these help map makers to quickly make maps of areas affected by natural disasters. The maps are then used to monitor damage and organize rescue efforts. So you can see here, this whole area right here was kind of wiped out, right? And then these darker areas, or darker green areas, are now a dark green, which means they are not necessarily destroyed, but that they are definitely damaged. So one series of satellites used to collect data about Earth's surface is the Landsat group. So Landsat 7, which was launched in 1999, completes a scan of Earth's entire surface every 16 days. So recently, it was used to map the coastal waters of the United States, comparing today's data to similar data collected 18 years ago. And scientists recognized changes in coral reefs. So similarly, comparing data of Minnesota's wetlands will help in tracking climate changes and perhaps the effects on bird populations that migrate there. Landsat has been used to contribute the GIS database as well. So a pair of satellites, TOPEX, and its successor, JASON-1, have been used to determine ocean topography, circulation, sea level, tides, and climate change. So using radar, a signal is bounced off the ocean surface to measure bulges and valleys within 3 meters. Figure 17 shows ocean surface change due to El Nino and La Nina. So if you look here, you can see the image that you get when you bounce that signal off. So a device that uses sonar to map the bottom of the ocean is C-beam. C-beam is mounted on board a ship. Computers calculate the time a sound wave takes to bounce off the ocean floor and return to the ship. This gives the operators an accurate image of the seafloor and the depth of the ocean at that point. C-beam is used by fishing fleets, drilling operations, and scientists. So as you can see, maps are used not just to get to a certain place and back, but it also can tell you about the land, mountains, what type of area you're in, if you're surrounded by forest or field or flat land. So maps have many, many uses, and although it continues to change how we collect data, the map part is always remaining the same.